In this video, I'm going to show you how we handle the uncertainty in the cost estimate for Matagorda Bay, as well as how we could handle the uncertainty in the benefit-cost ratio estimation. So the project that we described is basically a navigation project, creating a new channel, so dredging is a key component of the cost estimate. You are looking at CDEP, which is a model developed by the Corps for use by the Corps. It's maintained in the Walla Walla district, and this is an actual application of the model. Back in 2000, I was involved with a proof of concept project to show that cost could be estimated by accounting for the uncertainty. So that's what you're going to be looking at here. And I'm not going to go into great detail. There are many tabs down here at the bottom of this model, and they have all sorts of work units. We're not going to explore that. We're going to stick with this tab right here, which is what is used to calculate the unit cost of dredging up here. So there are a number of things, and we're going to begin right here with indirect cost. I'm going to put my cursor in this cell and pull up the defined distributions so we can look at the distribution in here. When we began this proof of concept, the district was using 15% as the contractor's overhead. When we asked the estimators if they were sure it was going to be 15%, they would give answers like pretty sure, but with a little discussion it was clear that there was no guarantee that it would be 15%. It could be more, it could be less, and so we worked with them to identify that. Back at the time, they said they were quite confident, based on past experience, that it wouldn't be less than 13%. They were also quite sure that it wouldn't be more than 16%. So given the range of 13 to 16%, we asked what would be the most likely value, and they said, of course, it's the 15% that they used in their estimate. So essentially what happens in a triangular distribution is we have 3 points. One is raised up here, is more likely than all the others. Then we get a ruler and connect the 3 points, and we have a probability distribution. Now when I say we get a ruler and connect the points, that's not literally what happens, but that'll be good enough for our understanding for the moment. And so this is a picture of what we believe to be true about the contractor's overhead. We're basically saying we don't know what the contractor's overhead is, but it's going to be somewhere between 13 and 16, most likely 15. And so when I close this and I hit F9 to recalculate a value, what the computer basically does is it reaches into this number line between 13 and 16, it pulls a number off and it sticks it in this cell right here. And then it uses that number to complete all the calculations that lead to this value up here that we're interested in, this $3.16 at the moment. So let me close this. We're going to turn on the dice now, and you see it's 15.4, 15.5, 14, 15, 14.9, and so on. Each time I hit a recalculate, the computer goes into this distribution, pulls a number off the number line, and sticks it in here. But it pulls the numbers according to this rule that we have drawn. So numbers over here, where the distribution is not so high, don't get picked as often as numbers over here. More numbers are going to be drawn from the fat part of the curve than from the skinnier parts, the corners of the curves. Okay, so we don't know what contractor's overhead is. If we were to go down through here, we would find the same is true for contractor's profit and for many other values. We don't know exactly what they're going to be. So there are distributions throughout. Here is an area where the uncertainty is particularly important. What materials comprise the channel bottom for this new channel that's going to be dredged? If we have mud and silt that's factor 3, you could practically put a straw in there and suck that out. On the other hand, if we have blasting rock, that's going to take dynamite to remove it. So this is a really important uncertainty. How much of the material is factor 2.5, how much is a 2, how much is loose sand, and you can see once again that we don't know. There's uncertainty there. And this uncertainty has a tremendous cost impact. So you can see how these values are all changing. So let's scroll down through here, and not to belabor the point, but there are many things we don't know, like what percent of the hours in a month will the pumps be able to run? Well, that's uncertain also. And because all of these inputs are uncertain, this value here is uncertain. So if you ask me what is going to be the unit cost in Matagorda Bay for Plan 1 and Reach 1, my answer has to be I don't know what the cost is. And if you say, why don't you know? I would say because I don't know what the contractor's overhead is. Now, you're going to hear me say I don't know what the contractor's overhead is many times, but that stands for all of these things. I don't know what the profit is. I don't know what the dredging prism is. I don't know what the composition of the bottom is. I don't know any of those things. So it would be naive to think I could tell you this. So we're going to run a simulation, 10,000 iterations, start the simulation, and you'll see that begin. And this is my estimate of what the unit cost could be. You'll notice up here on the right hand side that I have a minimum at the moment of $2.35, a maximum of $4.10, and I am zeroing in, the mean is about $3.06. But this is a picture of what that probability could be. If we were to choose that $3.06, that number, that mean, the one that we kind of gravitate toward, let me type that in here, $3.06. There is a 49.3% chance that the actual cost will exceed that. So are you comfortable using that as the number to use the mean when there's about a 50% chance that the value is going to be greater than that? I certainly wouldn't be. So we're going to talk about how you present data later, but I'll tell you right now that the best way to do this is you take the minimum value, 235, and the maximum value, 421. We use the median value, which divides that range in half, and then we would use the 25th percentile, $2.85. That's the first quartile value, and we would use the 75th percentile, $3.26. And so anytime that we talked about the cost of dredging, Plan 1, Reach 1, whoever asked would see those 5 numbers over and over and over. They would see those 5 numbers. And the hope would be knowing that the maximum could be $4.21, and knowing there's a 50% chance the price is greater than $3.06, those folks above us who are making decisions would not focus in on a number. So we have a distribution here. This is the output to CDEP. I can grab this distribution. Okay? Now, this was for Plan 1. When I go to the next model, which we're about to do here in just a second, excuse me, I have to subject you to my searching here. We're going to grab our next model, and this is a project cost estimate. So you'll notice that we have the typical accounts, lands and damages, relocations, and down here we have navigations, ports, and harbors. This is where the dredging cost appears. You'll notice Reach 1, Reach 1 here, and there is a unit cost for Reach 1. This is not Plan 1, so the numbers won't align exactly, but hopefully you get the idea that what we did was we took the output from our CDEP model. We took that output, one more time, we took this distribution as a whole, and let me close this, and we stuck it in here. So when I use define distributions now, you'll see these are that distribution. It's just displayed as a cumulative distribution this time because that's a little neater display. So that's been done for all of these distributions. All of these cost estimates came from runs from CDEP. These values here, the amount of geotubes, let's take a look here. This was estimated as between 1,250 feet and 1,550 feet. Actually, what we did was we took the analyst's best estimate of 1,400 and asked them to provide a bound because they knew it was not going to be exactly 1,400 feet. So they said it could be 10% less. So we take 90% of 1,400 to get the minimum. That's 1,260 feet. Could be 10% more. So that's 1,540 feet. So somewhere in there. And what you would have for all of these values in here is a distribution. Now what we're interested in, of course, is the cost here. So we'd like to know what's the cost. And the answer to what's the cost is I don't know. And if you said, why don't you know? I'd say because I don't even know what the contractor overhead is. And because I don't know what the contractor overhead is, I don't know what this dredging cost is. And oh, by the way, I don't know how much geotube we're going to need or what a geotube is going to cost. So we can take a look here so you see there are many kinds of distributions that you can use here for these types of data. So we place our cursor in here and we're once again going to start a simulation to see what the cost could be. You'll notice up here in the upper right, the minimum is 14.1 million. I have a maximum of 26.6 million. This is my estimate of the cost. So what is the value? The answer, once again, is I don't know what it is. That's honest. Why not? Because I don't even know what contractor overhead is. So if we were going to display these values, we'd say it's no less than 14.1 million, no more than 26.6. The midpoint is 19.2 million. That means there's a 50% chance it's more than that, a 50% chance it's less than that. If we scroll on down to our first quartile, 17.9 million, there's a 75% chance it's going to be more than that. If I go to my 75th percentile, the third quartile, there's a 25% chance the project will cost more than 21.1 million. I would always present those five numbers. Whenever anybody asks me what the cost is, I'd say I don't know. Here is our summary of what it could be. And I would make sure that anyone who gravitates toward that middle number, the median, understands very well that there is a 50% chance that the cost could be more than that. So once again, I have a distribution of cost here. I can capture that distribution, and I will for the next model. So let me close this last one. Now what we have here is the benefit cost analysis. So let's take a look at the benefits. One category of benefits was aids to navigation. As vessels come out of that GIWW and swing down close to the barrier island there, they are constantly knocking out the aids to navigation. The Coast Guard says they pay $110,000 a year for that. Of course, that value is uncertain, but it's so small and so trivial that we just leave it as a fixed value, 110,000. So you don't have to go crazy with replacing every single quantity with a distribution. Sometimes it's not worth the effort and the magnitude of things. Another category of benefits would be O&M cost reduced. Right now, dredging that channel that is used requires constant dredging, some annual maintenance dredging and some major maintenance dredging on a 3-year cycle. If the new channel was constructed, major dredging could be reduced to a 12-year cycle, and the maintenance dredging, the emergency sorts of stuff, would also be greatly reduced. So there's a tremendous amount of benefits that come from O&M cost reductions. And then there are the benefits that come from time savings. By constructing the new channel, The vessels moving across this area would save money. Now, you'll see here in column B, we have the present value for Plan 4, and then we have the average annual equivalent values for Plan 4. If you're an economist, you know these are two equivalent ways of expressing the same dollar values. We're going to look at present values because that's what people seem to be more familiar with when they don't have that economics background. So you can see here in this estimate, we have $31.5 million in accumulated benefits from this project. As I explore the possibilities, hitting my recalculate, you can see the uncertainty in the benefits. But they seem to hover between 30 and 33 million, somewhere in that area. Down below, we have costs. We have construction cost estimates. This is Plan 4. This is different than the plan that we were looking at, so you're not going to see the same magnitude of dollars for this particular plan. But it's the same idea. What we have done is taken this value right here. This was the output from that last cost estimation model. We insert that distribution into here, and so we have a complete description of the uncertainty of construction costs. We've also looked at O&M cost for the new project. They are also unknown. So the construction cost and the O&M cost together give us a total cost, and as we recalculate, you can see that total cost varies also. We don't know what it is. Why don't you know what that cost is? Because we don't even know what contractor overhead is. Why don't you know what the benefits are? And that's because we don't know what the visibility conditions are, what the wave conditions are, what the load is that's being pushed by the towboat operator, and so on. Down here we have some decision criteria. Net benefits is the benefits minus the cost. So this project produces, you can think of it if you will, as a profit of $12.6 million. If we take the total benefits divided by the total cost, we get a benefit cost ratio of 1.68. So what we're going to do now is we're just going to look at this. We're going to ignore this alternative benefit cost analysis. That excluded the O&M cost reductions. So without that, that's looking at the benefit cost ratio. So we'll take a last minute peek at that, but for the moment, let's focus on this right here and see how much money this project might make for us. So once again, we're going to start a simulation. We're going to calculate this 10,000 times. And you begin to see now over here on the right, the minimum is an $8.6 million profit. The maximum, the profit could be as high as 18.5 at the moment. The mean is beginning to stabilize at about 13.9. So these are the net benefits. These are the net benefits to the project. Let's take a look at the benefit cost ratio, because that's perhaps the magic number that you all would like to know. So if you ask, what is the benefit cost ratio for this project? The answer is, I don't know. Why don't you know? Because I don't even know what the contractor overhead is. Okay, and that is symbolic of the hundreds of things that are uncertain that go into a project like this. If we were going to describe it, we would say it's no less than 1.39, no more than 2.24. The median is 1.79, but remember there's a 50% chance it's more than that, a 50% chance it's less than that. The 25th percentile is 1.73, the 75th percentile is 1.86. So if we're going to report the benefit cost ratio, you get those 5 numbers all the time. That way, anybody who looks at this cannot help but know that we don't know this value for sure. And no, we're not going to pick one of those. If you are a decision maker, you need to consider this uncertainty and see what you think. In this case, that might be very good news. It says that the likelihood that this project has a benefit cost ratio less than 1 is 0 based on our estimation of 10,000 different possibilities here. Okay, so this is the benefits for plan number 1. the benefit cost ratio. Let's add plan number 2. And you see plan number 2 has a slightly different benefit cost ratio. Since it's to the left of the red, we would tend to think that project red is going to be a better project. Let's add one more. Plan 6. You can see the green here now. The green has less of a probability of these low benefit cost ratios. It doesn't seem to be quite as good on the upside. The red plan still has a better upside, and the green plan looks like it has a slightly worse downside. If we change the look here, I right mouse click on the graphic, choose graph options, and say show this as a cumulative ascending. Now I can see that values to the farther right, they are bigger benefit cost ratios. So the plan that's farthest to the right is the best plan. Let me add one more. We'll add this plan here. And we see that didn't change. So it looks like the red plan is clearly the best. There is down here, there is some chance that when it gets to the downside, the green plan has the best downside. The green plan has the highest benefit cost ratio. If the worst conditions prevail, the green plan would be better than the red plan. Otherwise, the red plan is best. So making decisions with this kind of uncertain information is going to be different as well. Okay? Before we close, let's take a look at this alternative benefit cost analysis. Suppose for some reason O&M cost reductions didn't exist, that there wouldn't be cost reductions. Let's pull up these results. Here we have a slightly different situation. Now if I pull my delimiter over to a benefit cost ratio of 1, we see there's a 54.4% chance that this project will not have a positive benefit cost ratio. It would be less than 1 and would lose money. So that sort of information is not information that you can get from that one value that we use. This has been a little overview to how uncertainty could be used to talk about benefit cost ratios, decision-making criteria, cost estimates, benefit estimates, and all of those sorts of things. So let's have one more look before we go. What is the benefit cost ratio? Everybody together. I don't know. Why don't you know? Because I don't even know contractor overhead. This is a much more honest way of doing our analysis. It's a much more honest way to support decision makers, and they're not ready for this. The only way they're going to get ready for this is if we teach them that there's no such thing as the number.